Markus is Director of Technology Management at Autotech, which is the third most sustainable corporation mentioned in 2014. He has over 400 publications in books, encyclopedias, journals, and conference proceedings. Main author of the book Metrics of Material and Metal Ecology. And I personally know him for many years. He has been contributing to UNEP's International Resource Panel with a wonderful report on metal recycling. And I think you have been in all our World Resources. I cannot imagine a World Resources Forum without Markus. So we really like him, and you will find out why.
Good morning, ladies and gentlemen. Thank you for the introduction. I'd just like to take these 15 minutes to talk a bit about circular economy, but having started, I just saw the company name Anglo American, where I started in South Africa many years ago, as the basis, and try to weave in that basis to innovate that circular economy. We just have a good look at that figure because it will appear 3 times in the next couple of sheets or so. We speak very fast and easily about circular economy. Well, what are the real issues to make it happen? We speak about element and material criticality, but we forget that we need an infrastructure to make it happen, and it has to work economically. We speak about material-centric recycling, but we forget that our products that we want to have in a circular economy are extremely complex minerals. Just think of the telephones that you have in your pocket. So we coined the word product-centric recycling in that UNEP report that Bas mentioned a moment ago. Just look at those figures at the background. As I said, I'll come back. Simplicity, complexity, recyclability index, lifetime of that product. Just keep that in mind. The question I'd like to ask, if you would take those 2 products that I showed a moment ago, the old globe and the LEDs, which is better from a recycling point of view? Obviously, it's a no-brainer that the one has got a very much better energy sort of footprint over its lifetime than the other. But does it have that from the recycling point of view? As I said a moment ago, these products are becoming so complex that their mineralogy and the recovery rate of the elements back from it becomes very, very difficult, as this figure tries to show. So we had a simple world, but was it necessarily worse than we are now? This is a figure that comes out of one of the documents from the EU that tries to, in a very simple way, show what sort of a circular economy sort of entails. Obviously, you'd like to minimize that waste, but if you really want to innovate the system, like any process engineer that I am, when we design a plant, you like to obviously maximize recovery, minimize the waste. We've always been doing that. We've always tried to optimize the plant. So there's nothing new really to it. But that implies, and if we want to do it on a real sort of metallurgical minerals type of plant, where this circular economy is just a larger version of that, we understand all the waste. It's no use just drawing a simple figure like that and hope that you minimize the waste. You really need the detail. You really need to understand that. I believe the metallurgical and minerals processing industry has an extremely important part to play in innovating and enabling the circular economy thinking. A slightly more complex version of that previous one is one that I'd like to delve on, and just to illustrate those points I made. We see in many of the EU documents, we have to do product design for recycling. But the products have a functionality. Materials are together because of that functionality. It's a question I asked yesterday about the carbon material in the electrodes of batteries. They are there for a reason. To get them out is extremely difficult. So on the one hand, it's good the material is there, but from a circular economy point of view, how good is it? How much can you do from product design point of view? But I do believe, like we do in classical minerals and metals processing, we use simulators to understand that. That's the next part of that drawing is actually, if you want to enable the system, innovate in the system, you have to fundamentally understand it and simulate it. From that, you can ultimately determine from each element of what the deportation of each element in that system would be, as the bottom diagram would show. And then from that, we call it green printing, actually get the footprint of this whole product design that you're doing, and what is ultimately achievable, what the limits are, in other words, of this whole process. We'll delve in that a bit further in a moment. Coming back to that figure, the green, there's a list of elements and compounds that you would find in these products, specifically the LED. Many of those elements do come from base metal mining and metallurgy. You need that. They're also the minor elements from the base metal, copper, zinc, lead in this specific case, and are required there. So that link to the mining sector is important. And if the product is so complex that you cannot recover them, you have to be very, very careful that you balance the mining, which is required, with obviously the recycling, but you cannot recover everything. So you'll have to very, very carefully look at that. But please note, you need the metals, you need the minerals to be able to achieve that. And you have to be very, very vigilant that you maintain that understanding that you can recover those, that you have an infrastructure that can recover those. Coming back to just one sheet from Autotech, it was said yesterday as well that technology is there. Well, it's not always there, but in this case, to process various waste types from metallurgical operations, from e-waste, from copper scrap, etc., from batteries. It's there. We've built about 20, 25 odd plants that do that already, as here are a few shown. Japan, Dowa, it was mentioned yesterday, gold recycling. It's among others done in that plant in Kosaka. Then in Sweden, Germany, China, and South Korea. By the way, the technology used is an Australian one, developed here starting about 40 years ago. And it's had a worldwide usage in these sort of applications. A very interesting one for you to know as well, which sort of really embodies the spirit of this conference, is circular economy within a company. It's this one, it's Port Pirie, down south, where the major change is an Autotech TSL that's going to be the workhorse to do certain activities in that, but not just from a Port Pirie point of view, but from a Near Star point of view. So very, very relevant to look at these bigger solutions, but ultimately embedded in a very, very solid techno-economic base and understanding where each element goes so that you can make a business case out of it. And obviously an economy of scale to do that. Interesting, I think it might be the first really large smelter being built again in this country for some time. Coming back to that complexity picture, having grown up understanding what minerals are, always having had a respect for them, their complexity and their beauty. On the left-hand side, many elements, and even that is often a challenge to get the maximum benefit and recovery of all the elements from that. But taking the modern products as shown there, with many more elements with the functionality of connections, challenges the recovery, the circular economy. How much can we truly get back? As I always say, you will, depending on what process you use, you will sometimes win some and you lose some. And depending on what your process is in another one, you will lose the others and get another sweet out. So it's always a very, very complex understanding and game Not just a simple little diagram on a figure, but a complex understanding of what each element does in that system. I just show that to here specifically also for the research community, and it's work we did together with Swinburne in Melbourne a couple of years back. You need to understand the physics in the reactors to actually do that. You cannot go beyond the laws of physics. And that's what this just tries to show. Circular economy needs, in other words, the deep understanding to really innovate. And also the metallurgists in this case are truly required. What I also like to specifically address, many years ago, we already, about 10, 15 years ago, tried to make people aware of this complex web of metals, where people were sort of drawing little diagrams of single elements on a piece of paper and trying to express that that's a circular economy. They're highly connected, and we have to understand of a LED lamp, say 40 different elements, and understand where they go to truly close the loop, truly understand the circular economy in that specific case. So what is extremely important, and I, being an extractive metallurgist, always say, without metallurgy, there is no circular economy. You need to understand that. You can't just buy these elements. If you want to do circular economy, you need to smelt, you need to remelt, you have to recover. You need metallurgy knowledge. So that metallurgical infrastructure criticality is extremely important. Not just material criticality, but actually have the capability to do it. And you don't learn this in a textbook. It takes many years to build. It takes a day to destroy. And that tacit knowledge is gone. So extremely important, anywhere in the world, to ensure that that knowledge is maintained. I'm coming to sort of the last sheets of this introduction here. Perhaps a busy sheet, but this is where we are at the moment, to go from this classical mining metallurgy point of view and transporting that to design for recycling. There are many glib design for recycling activities out there, but then I usually ask, do you know what the effect is of that complex mineral in your recycling chain? And then you often get blank stares. What we've tried to do, we've taken a product design, we've put it through a simulator, as I've shown in one of the first sheets, understand where each element is going in the system. If the system changes, that element distribution changes. The economics change, and ultimately also do the footprint. So what you see at the bottom right is 5 redesigns of an LED lamp and analyzing that each time. And that's really understanding fundamentally what is possible in that system. How much can you truly recover? And that's the main topic of my talk. Understand the fundamentals and really make it happen. So ultimately, just standing then there and talking about big simulators, we've come up, actually a couple of 2-3 months ago, we published this paper. It's taken about 10 years. Analogous to the energy rating of products, we've come up with this rating for recyclability index based on simulation. Not just some hand-waving design for recycling, but understanding where each element goes and comes from. If you do that for an LED lamp, you'll find that the recyclability is rather low, which is a no-brainer. You saw it from those X-ray pictures. But this is taking the information, the design information, informing public. So we heard yesterday evening, yes, Google is doing big data analysis, but they should at the same time also provide the consumer, the buyer, with this type of information based on solid physics to really make a good decision. If that doesn't happen, we're just consuming. Big data is just making us consume more. We need to inform, and this is the way to take complex physics in a very simple way. So my final sheet then, I've been always trying to understand the beauty in the simplicity of systems. I ask you now once again, if you would take the classic globe and you have the LED, would it not be possible, if we have clean energy, from a material point of view, why not use the globe? Why do we go so complex? Because our energy is so dirty. So that balance of really simulating the system, energy plus materials together, and understanding the recyclability of the use phase, the simplicity of the product, getting the materials back at the same time, would lead us better down the path of resource efficiency. So in other words, integrating the web of energy with the web of materials. In other words, trying to do the Internet of Things in a very solid, fundamentally based basis. So basically what I'm ending off with is system innovative thinking, modeling systems, is basically an engineering discipline. That's what we teach engineers. I think it's, I always say that, it's really what we require to do, bring in the engineers as well in this discussion to make it really truly happen techno-economically. In other words, keep the infrastructure running and doing what our company tries to do, the sustainable use of Earth's natural resources. It's pretty hard. Our CEO put that mission statement there. We're trying to make it work. We're a bunch of engineers there trying to do it. Thank you very much.